You're watching a Channel 98 NBISD TV production.
Hey, welcome to another fantastic episode of Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy, as usual. Today we got lesson 27 in store for you. One of my favorite numbers, okay? And we're doing one of my favorite things. We're going to be building things. That's right. We're building functions from other functions. Okay? So put on your overalls, download those worksheets from the district website, grab a sharp pointy pencil, and stick around and learn how to build functions out of other functions today on Deja Vu. It's Algebra 2. All right, lesson 27. We are quickly approaching lesson 30. Today we're going to be building functions from functions, as I mentioned on the intro there. And we're going to start out by building functions by using transformations. And it's going to tie into something that's been a recurring theme on previous episodes. We're going to reintroduce the idea of a parent function. Okay? Now what a parent function is, it's just a basic representative of a particular type of functions from which all other varieties of that same function can be generated by using a sequence of transformations. Remember, we have dilations, the stretches horizontally and vertically. We have the reflections, x-axis and y-axis. Then we have the translations or the shifts, and we can shift it horizontally or vertically. And a change in the equation is going to change the graph in a particular way. And it doesn't matter what function we're starting with, doing the same thing in the same location in any equation will have the same effect on that particular graph. And so the parent function is basically the graph that we're starting with. Okay? Here's a parent, there's a child. That child wants to do math, and maybe the mother is not letting it. It's time to do something else. But it looks like there's a little resistance there. Anyway, let's move on to this. What we're going to do is create functions from new by using a sequence of transformations. So remember, a function is like a machine. It's a machine that takes an input and drops it in and makes some type of numeric change to it. So we input a number, here's the machinery. In this case, the machine multiplies your input times 2 and then adds 5 to it in that order. And then we get an output. Okay? So this would be a linear function, and the parent function would be y equals x. X is the input, multiply it by 2, which would give you a new slope, and add 5, which is your new y-intercept. Okay? So let's look at what type of parent functions we've encountered already this year and kind of put them all together. All right, here's some basic examples of some parent functions. Of course, we have f of x equals x. That's x to the first power. Those are linear because they graph as lines. Now, the parent function of x has a slope of 45 degrees, or a slope of 1, and it passes through the origin with an increasing slope. The quadratic x squared is decreasing to the origin where it has its vertex at the relative minimum, and then it increases to the right. It has y-axis symmetry. That's x squared, quadratic. Then we have the square root function, which is half of the inverse of x squared. It's just the positive version of it, because if we had the negative version down here, it wouldn't be a function. So we have the square root function, square root of x. And then we have these, and we've dealt with these on relatively recent episodes. We have b to the x, which is your parent exponential function. If the base is greater than 1, it's going to be looking like this. It's going to be exponential growth. It grows very rapidly. It has a horizontal asymptote on the x-axis, and it passes through the point 0, 1, because b to the 0 is 1, if b is not 0. Then we have the inverse of b to the x, which is log base b to the x. And it's basically the reflection of this graph across the line y equals x, and we get this graph right here. It's a monotonic increasing function passing through the point 1, 0, because its inverse exponential passes through the point 0, 1. It also has a vertical asymptote on the y-axis because its inverse has a horizontal asymptote on the x-axis. So there's a parent function. And then we had this one when we were talking about rational functions. It's the reciprocal function, 1 over x. It just reciprocates your input. And this is the one that looks like a hyperbola, if you know what that is, rotated 45 degrees. It lives in quadrant 1 and quadrant 3, and it has a vertical asymptote on the y-axis, horizontal asymptote on the x-axis. Now, it's a good idea to start memorizing what these basic characteristics or what these basic graphs look like, because your teacher in class might expect you to sketch transformations of these without a calculator. And let's do that right now. Okay, example 1. What we want to do is we want to sketch this function. It's f of x equals negative x, or negative square root of the quantity x minus 1, which is under the radical, and this minus 1 is outside. So the first thing you want to do is identify what the parent function is. Well, the radical is a pretty good indicator that this is a square root function. So what goes through your mind when you're trying to sketch this? Well, you think of the parent function y equals square root of x, and you imagine it in your head. It looks like that, right? Now we go through and we look at the transformations. The negative out in front is an x-axis reflection. It does the same thing to any graph. Remember when we had negative x squared? The parabola opened downward. It reflected across the x-axis. Same thing with any function. So that's going to take this graph and reflect it across the x-axis. I'll draw it as a dotted line. So that's where we are. That's the first transformation. We're going to do them as a sequence. The minus 1 on the inside of the function is affecting the x values, and this is going to be a shift to the right 1 unit. So this is right 1, and so this graph here would move over to the right 1. Every point moves to the right 1, but it's real convenient to follow the original origin. So it's going to be over here to the right 1. This minus 1 is outside the radical. That's affecting the output values, or the y values, and it's going to move everything down 1 unit by subtracting 1. And so we basically reflect across the x-axis, move the graph right 1, and then move it down 1. And we have to do it in that particular order because, remember your dear Aunt Sally, multiplication and division have to be done first. A negative in front is really a negative multiplier, so we have to reflect it first. And then the minus and the pluses are the addition and subtraction. Those are the shifts. Those have to come after any dilations or reflections. So here's what we'll do. I know that I have a basic shape that's going to be opening down and to the right because I reflected it, and I'll move it right 1 and down 1, and I'll just sketch that right here. So we draw a brand new x-axis, right 1, down 1. That's where the original origin was, and from there we can just draw our shape decreasing, and it does go down to negative infinity, but at a less quick rate, okay, at a decreasing rate. Now what we want to do then is list the domain and range. So the domain, we're going to write it like this. It's going to be the set of all x's such that, well, we can't go to the left of 1. We can have 1. This is actually at 1. And everything to the right of 1 also works. So x is greater than or equal to 1. That's the domain. The range is the outputs, the set of outputs. And notice our highest or biggest y value is down here at negative 1. And we have everything below that now. So we'll say the range is the set of all y's such that y is less than or equal to negative 1. Okay? So that means at 1 and to the right for the domain, at negative 1 and below for the range. And that's all you need right there for the sketch of the graph. It's enough to talk about the graph just by doing some simple transformations of a parent function that we've memorized. Okay? Let's try another one down here. We've got g of x now is 4 minus 3 to the x plus first power. Ooh, okay. So what's the parent function here? 3 to the x plus 1? Well, if you have a variable in the exponent, that means that your parent function is exponential. Yeah. And in this case, the base b is 3. So our parent function is y equals 3 to the x. Now, what should jump in your mind right there? It has a horizontal asymptote on the x-axis. It's bigger than 1, the base is, so it's increasing, and it passes through the point 0, 1. Now, it's sufficient to know where the general behavior of this graph, what it is under the transformations. So if you know what happens to the horizontal asymptote, if you know what happens to the point 0, 1, and you know what the basic shape is, you can sketch a pretty accurate graph just by following that information around. Now, what you want to do is try to get this into a transformation form that looks like this. G of x in general is going to be a times some function f of b times x minus c plus d. And if you can get it like that every single time, that ties into what we've been doing pretty much all year long. Your a and b are your dilations, your c and d are shifts. So I'm going to rewrite my g of x because it's not in that format. I'm going to write that as negative 3 to the x plus first, and then plus 4 at the back. So again, this negative in front is an x-axis reflection. We do that first. So it'll take this basic shape, and it'll reflect it across the x-axis. So now it's going to be decreasing from left to right, and it passes to the point 0, negative 1. Okay? Then the x plus 1. The plus 1 is in the exponent with the x. Anything that happens right there with the x is affecting the graph horizontally, That's going to move everything left 1, and the plus 4 is affecting the y value, so it's up 4. So if I could take this basic shape right here that passed through the point 0, 1, move it left 1 and up 4, I'll have my graph, and it'll have that basic dotted line shape. So here we go. We'll sketch it right here. What happens to the horizontal asymptote when we move it left and right? Nothing. It already runs east to west. But when we move it up or down, it moves the horizontal asymptote. Now, if you ever have any asymptotes on your graph, I would recommend sketching those in first because they kind of define the shape of the graph. So I'm going to draw mine. It was at y equals 0. Everything's up 4. So now it's up here at y equals 4. And I know my graph is going to fall somewhere down in there. Well, the old point, the y-intercept at 0, negative 1, is going to be moved to the left 1 and up 4. That's going to move it to negative 1, positive 3. I can sketch that in. Negative 1, positive 3. So now it's going to come in like this from the left-hand side, hit that point, and start decreasing. Now here's another thing you want to be aware of. You want to try and be as accurate as possible, even though it's a sketch. Notice I'm going to be crossing the y-axis here. I didn't cross the y-axis on the previous example. Y-intercepts are very easy to find. All you have to do is plug in a 0 for x. And you can do it to any version of the equation. Let's go back to here and figure out what g of 0 is. G of 0, that is plugging in a 0 for x, you get 4 minus 3 to the 0 plus 1, which is 1, which is 3 to the first, which is 3. So I get 4 minus 3, which is 1. That means that's my new y-intercept, and I can sketch that in right there. And now I have another point that's going to guide me through the y-axis, and it decreases like that. Ooh, there it is off the screen. So that's a pretty good graph. Now the x-intercept right here, that's a little bit more difficult to find. We're not going to do that today. But from here, and this alone, without a calculator, we can talk about the domain and the range. The domain is going to be everything that the x values take on, and this goes out to negative infinity, and that goes out to the right forever. So in this case, it's all real numbers. And every exponential function is going to be domain of all real numbers. Now the range, notice, is going to be affected by the horizontal asymptote and whether it lives above or below. In this case, it's below because we reflected it. So it's going to be all the y values, the set of all y's, such that y is strictly less than the horizontal asymptote's value, which was 4. It's not less than or equal to anymore because there's a horizontal asymptote there. And in this case, we approach 4 as we go out to the left, but we never actually reach it. So again, memorize the basic parent functions, know how the change in the equation affects any graph, and you can quickly sketch what the new function is and answer questions about it. Okay, now we can also create functions by combining one or more functions to create a brand new function. And we can do that by doing addition, subtraction, multiplication, division, or composition, which we'll do at the end. So let me illustrate what we're doing here. Let's take 3 functions, f of x, g of x, and h of x. And we're going to use the same functions for all these examples. F of x is a quadratic, g of x is a line, and h of x is a radical function, square root of x, parent function. Okay, first we have to learn notation. If I say f of x plus g of x, that just means I'm adding this function to that function. We can also write that, though, in this abbreviated notation, f plus g of x. And that's because f and g are the names of the function. X is the independent variable. So when you say f plus g, you're saying add f and g together, and it'll still be a brand new function of x. All right? Now, there's several ways to do this. We could do it horizontally, which is probably the preferable way if you're going to climb the ladder in mathematics. I'm going to go ahead and write down f of x from up here, 6x squared minus x minus 12. And to that, we're adding g of x, which is 2x minus 3. Now, we technically have a brand new equation. If you want, you can call that h of x. It's a brand new function combined from the other two. But we also want to combine like terms and simplify it. And when you do that, you want to write it in descending order of degrees. So I have a 6x squared. If you want to cross it out as you use it, that's good. I have a minus x plus 2x. That's going to give me a positive x, and those are gone. And then you have a negative 12 minus 3, which is a negative 15. So I get another parabola that's 6x squared, but it has a different y-intercept and a different value coefficient of x. Okay, so it's a brand new function. I've created a brand new function from combining two of them. Okay, well, we can also subtract g of x minus f of x, or g minus f of x. I'm going to do this one a little bit differently. I'm going to subtract these vertically. You may prefer vertically, especially in the beginning here. We start with g, which is going to go on top. 2x minus 3 minus, now you've got to be careful when you're subtracting, especially polynomials, because you're subtracting multiple terms, which means you're going to have to distribute that negative. So I'm going to put parentheses here, and I'm going to have a 6x squared minus x minus 12. Now when you subtract or add vertically, what you want to do is you want to line up in columns vertically your like terms. Okay, so I have my x's and my constants, and I don't have anything up here, so if you want to put a 0x squared as a placeholder in the top, that's fine. Now we subtract top minus bottom, like terms. 0 minus 6 is negative 6x squared. 2x minus negative x is really 2x plus x, which is plus 3x. And then negative 3 minus negative 12 is really negative 3 plus 12, or 12 minus 3, which is plus 9. So adding it vertically works as well. Remember, when you're subtracting, you can distribute. And if you prefer to do one extra step in here, distribute the negative to all three terms and make it an addition problem, that would work well as well. Okay? One last one, and we're going to take a quick break here, is multiplication. F of x times g of x. This is multiplication. You carefully want to write down your functions. There's f of x times g of x, which is 2x minus 3. Now, if you want to stop there, that's fine. Technically, that's a brand new function. If your teacher required you expand it out, you can't use FOIL here. FOIL only works for the product of two binomials, so you just have to systematically distribute this first one to both terms there. So let's quickly do that. That's 12x cubed minus 18x squared, and then you move on down the line. The next one would be negative x, which gives you negative 2x squared plus 3x, and then finally you have this negative 12 distributing, and you get negative 24x plus 36. And now you can go through and collect your like terms. You have 12x cubed. You got minus 20x squareds. Let's see, you got minus 21x plus 36. And that's an expanded version. We get a cubic polynomial when we multiply a quadratic and a linear equation. Time for a real quick break. Don't go anywhere, though, because we're going to be right back. While you're gone, as usual, think about this. Why is a dog with one lame foot like adding 6s and 7s? The answer when you get back.
So, Sarah, what's going on here? Sarah? Sarah?
She won't answer you. Or she can't.
Why not?
This is the way it's been since she started smoking pot. She's all lazy and boring and... You know, we used to have so much fun together.
And now?
This is what we do.
It's easy to tell if you've had way too many. But what if you've had just one too many? Buzz driving is drunk driving.
Welcome back to Deja Vu. It's Algebra 2. As usual, I'm your host, Kevin Corpy, talking to you today about building functions from other functions. Adding, subtracting, multiplying, dividing, and composition. Okay. Now, why is a dog with one lame foot like adding 6s and 7s? Well, it's because he puts down 3 and carries the 1. Lame foot, lame joke. One thing that's not lame, though, is the math. Let's get right back to something we can count on. All right, we can also make brand new functions by dividing them. In this case, I have f of x divided by g of x, or again, using the same notation, f divided by g of x. Now, remember, in this case, we're creating a fraction with a potential variable in the denominator. So we might be looking at dividing by 0, and we want to find those values that make us divide by 0 and say, hey, those guys are not in the domain. But let's go ahead and set up the equation first. F of x, if you remember, was 6x squared minus x minus 12 divided by g of x, which was 2x minus 3. Now right there, we've created a new equation. It's a rational function, the ratio of two polynomials. Let's quickly look to see what value of x makes the denominator 0. If you set 2x minus 3 equals 0 and solve, you get x equals 3/2. That's the singular value that makes a 0 in the denominator, so x cannot equal that. That's the only value that's off limits in this new equation. Well, can we simplify that? Well, simplifying rational functions, you remember, comes down to factoring the top and the bottom completely, the numerator and denominator. Now, if I'm going to be able to divide out the factor 2x minus 3, I have to be able to factor the top as 2x minus 3. So that might give you an aid as to what the top might be if it actually does factor. So if the top is 2x minus 3, to get a 6, I have to have a 3x. And to get a 12 from a 3, I have to get a 4. Okay, so sometimes anticipating that it factors with 1 in the denominator helps you factor the numerator. And we just need to worry about the sign. It has to be plus there. Okay, so now if we divide these out, the 2x minus 3's do in fact divide out, and we're left with a more simplified version, 3x plus 4. However, we are still not allowed to plug a 3/2 into this equation of a line. It'll work, but remember that wasn't the original equation. So in this case, we'll have a whole or removable discontinuity on the graph of 3x plus 4, the line. And that's what the actual equation is. Okay, now composition is a little bit trickier. That's not multiplying and dividing. It's actually sticking one function inside of another function for x. X is a variable, and you can plug a number, another variable, or another variable expression into it. And that's what we do when we have composition of functions. So in this case, I have f parentheses g parentheses x. We read that as f of g of x. Okay, now the shorthand notation for that is this. You might realize or recognize that as fog of x. But it's not fog of x at all, because that's not really a letter, a 0. It's an open circle which can be thought of as an O for the word of, f of g of x. Okay, now here's the easiest way to do this. This is not multiplication, even though there's parentheses. Okay, it's composition. G of x is sitting inside f of x. If you want to show it like this, that's f of, and then put the g of x right there really small. Okay, that's what it is. Now what does our f function say? F function says to take your input, whatever it is, and multiply it by 6 after you square it, minus your input, minus 12. So what can help you in evaluating these composition functions is you could start with the outer function, which is my f function, and everywhere you have an x, put parentheses, which are placeholders for your x, and then all you have to do is wherever you have parentheses now, you're plugging in a g of x. But what is g of x? G of x was 2x minus 3. So now you can come back through there, everywhere you have parentheses, and put 2x minus 3, 2x minus 3. Okay? You're plugging 2x minus 3 essentially in for x into the function f. And the thing that's confusing for some students is you're taking a function of x and plugging it in for x, and for some reason you think the variable should change. And that's okay if you want to do that. But it's okay to also plug in variable expressions of one variable in for that same variable. It's okay. Now in this case, we don't have time, but you could expand that out the way we've been doing, and you can get the expanded version of the new polynomial. But it still does create a new function, call it h of x. All right, one last one here, and we're going to move on to the end of the show. This one's a little tricky. We got h of g of f of x. Okay, so we have a double embedded function into our outer function h. F is on the inside, it's plugged into g. That result then is plugged into h. Now if you write that in the fog golf notation, if you want to call it that, it's h of g of f of x. Now you might see it written like this because it's a little bit more condensed to present the work, but it's much easier to actually evaluate these expressions or create these new equations if you write it like this, because it makes more sense to what we're actually doing. So let's kind of work from the inside out. I've got h of g of f of x. Okay? I'm going to go ahead and do this one slightly differently. I'm going to start on the inside here. What is f of x? Well, f of x is 6x squared minus x minus 12. Didn't leave myself much room. Let me zoom in for you. So all I've done is I've replaced f of x with what it's equal to. Everything else is the same. Well, now, what does g of something means? That means that in my function g, I'm going to plug this in everywhere I have an x. So that's h of, and what is g of something? Well, g of something is 2x minus 3. So it's 2 times something minus 3, right there. And what am I going to plug in right there? Well, I'm plugging in 6x squared minus x minus 12. Okay? So now I have this brand new expression, and I could expand it out if I want, and that's what I'm plugging into the h function for its x. Well, remember, h of x, the function, said to take the square root of your input. In this case, what's our input? It's all of this. So this becomes the square root of 2 times 6x squared minus x minus 12, parentheses, minus 3. Okay, so there you go. Now, this function right here, you can expand it out and you'll get a quadratic under the radical, but your domain might be different from what the original functions were because we're creating new functions. And in this case, if you look at the parabola, any value of x that's going to give you a negative y value on the parabola, you're not allowed to use in this graph because it's going to give you a negative under the radical, which is an imaginary number. So the domains and range do change. Okay, we're running out of time, so I'm just going to leave that for you. If you have questions about it, shoot me an email and I'll answer your question. Okay, let's move on to the end of the show, my favorite part of the show.
Deja Review.
Okay, here's a nice application of composition of functions. Let's say you're going to go into a new automobile dealership and you're going to buy a new car for $30,000. The dealer might offer you some money back, some incentives, if you will. And what they could do is they could offer you a rebate, like maybe a 5% rebate, which is a percentage back on the purchase price, or they can offer you a cash back discount, which is a straight amount of money that you get back after you purchase the vehicle. Okay? So a 5% rebate is really multiplication because it's a percentage, and cash back is really added and subtracted because it's a strict amount off the price. Okay? So what we could do is think about this. If our dealer was going to allow us to take both of those discounts, how nice. But we have to choose the order in which we take them. Is there a strategy to take the rebate and then the cash back, or the cash back and then the rebate, so that we end up paying the least amount of money for that car? Well, the answer is yes, there is. And we can represent that with piecewise functions. If we let r of x be the purchase price of the car after the rebate, it's going to be 5% back, so we end up paying 95% of the original purchase price, which for us is going to be 0.95x, where x is the purchase price of the car. We can let c of x for cash back of x be the cost of the vehicle after we get our cash back, which will be x, the purchase price, minus $1,000. Okay, so we've created two functions. One's multiplied, one's subtraction. What we're really interested in this case then is which of the following compositions is actually the smaller of the two numbers. Is it r of c of x, or is it c of r of x? Those are the two functions composed different ways. Now specifically in our example, if we said the purchase price was $30,000, this is going to be r of c of 30,000. Okay, that's taking the discount, then the rebate, and c of r of 30,000. That's taking the rebate on the inside first and then the discount. Now if you work this out, we're running out of time, so I'll go ahead and just give you the numbers here. R of c of 30,000 ends up to be $27,550. That's taking the discount, then the rebate. But if we take the rebate first and then the discount, we only have to pay $27,500. So in fact, we should take the rebate first and then get cash back after that, because we'll be paying $50 less ultimately for that vehicle. All right, we're about out of time on today's show. Everything happens so quickly when you're having fun. Hope you enjoyed yourself on today's show. Hope you learned a little bit about adding, subtracting, multiplying, dividing functions, and of course, the more interesting way to combine functions, composition. A little bit tricky, one function inside of another, but as anything else, it just takes a little bit of practice, a little bit of persistence, and you'll have it. It's a skill. Okay, what can I say? Practice makes perfect, or perfect practice makes perfect. So anyway, I'm rambling on here. Like I said, we're out of time. We're getting even further out of time. I'm going to go. Okay, until next time, I am Kevin Corpy, and I'm reminding you to do your homework.